Thank you, Jeff. And as you said, this is an equationless talk. I've designed it in case any school children came, but since there are none here, I can't restore any equations. So I hope I'm not disappointing anybody. Why have I chosen to speak about the early universe? Well, the universe is a very fascinating and strange place. And one could really say that the whole of human civilization, through the whole of human civilization, we've had a relationship with the universe in the sense that every human probably has looked up at some time in their lives at the night sky and wondered about the nature of the stars or whatever they were thought to be at the time that were visible to them in the night sky. And it's been a central part of human culture as civilization has progressed that we've been progressively able to understand more about what lies behind that night sky and to begin to uncover some of the marvelous constituents and things that are going on in distant parts of the universe. And it's true to say that the early universe is yet more strange and more interesting because, in a sense, it contains the seeds that lead to all of the things that we see later on. And that's what I hope to arrive at today. I hope to take you on a journey from what we see around us back in time towards the beginnings of the universe to try to update you about some of the current understandings and speculations that we have about the nature of our universe. Probably the first thing we can say about the universe is that it is big. This wasn't always understood. This is actually a 20th century development. We're quite familiar before the 20th century with the scale of the solar system, which at that time was very large. The sun, for example, is 150 million kilometers away, which is a long distance in Earth terms. But if you think in terms of light travel, that's a simple 8 minutes away, because light, as you know, happens to travel extremely fast at about 1 billion kilometers an hour. And if we go outside of the solar system and we think about the solar system's relationship to the galaxy that it's part of, we're about 30,000 light years away from the center of the galaxy, which is an unimaginably long time and an unimaginably long distance in human terms, but it's actually a very small distance when we think about the next step in the ladder, which is what about the distances to other galaxies. And it turns out that other galaxies are millions or even thousands of millions, i.e. billions of light years away from us. So the universe is a very large place in human terms. Not only are the distances large, but the numbers of constituents are huge as well. So if we look at our own galaxy, the Milky Way, and we ask how many stars there are, the sun is just one of them, it turns out there are billions of them. And each of the galaxies that we see, and we've seen billions of them, consist of billions of stars. So we have huge numbers piled upon huge numbers on scales which are actually very difficult to appreciate from our human experience. The universe is very large and it's extremely full of things, even though most of it is made up of empty space. Now, it's important to take a step back and ask how we know these things. It's easy to get a bit blasé, as if these pieces of knowledge were simply handed down to us. It took many centuries to uncover this. And perhaps one of the key steps forward was in the 20s when a number of astronomers, but maybe most famously Edwin Hubble, showed that what were thought to be aspects of our own galaxy, these nebulae that we're seeing, these kind of cloudy collections of stars in the sky, Hubble actually showed that these were distant galaxies. They weren't just part of our own galaxies. They were far away, and they contained many, many stars like our own galaxy. But he made an even more fundamental discovery than that. He came up with what is now known as Hubbles Law, because he discovered that not only were there many galaxies beyond our own, but they were actually moving away from us. So, and in fact, the speed of recession, the speed with which they were moving away from us, was growing with distance. And the inescapable conclusion from this is that the universe that we live in is actually expanding. In other words, not only is the universe big, it's getting bigger all the time, from all the evidence. And here I have a little cartoon just to illustrate that. If I choose a given instant of time and I track, say, 3 galaxies, this could be our galaxy, and there's a neighboring galaxy in the north hemisphere and another galaxy in the south hemisphere, And then a few thousand or million years later, I'd have a look to see how far those galaxies are away. I discover that they're further away. Both of them are further away from me than they were before. And as time progresses, the distance is increasing. And you need to actually appreciate that in terms of modern ideas of space and time, not only are the galaxies moving away from each other, not only are they moving away from us, they're all moving away from each other. Any galaxy that you're attached to, you'll see all the other galaxies moving away from you. And the only way that can happen is if the actual fabric of space itself is expanding, which is a truly revolutionary concept due to Einstein. Now, how did Hubble actually detect this motion of the galaxies? He did it through a very important phenomenon called the redshift of light. And we're all aware of this in our own experience in terms of sound waves. If you're standing at a station and a train approaches you and then moves away from you, the sound as it approaches and the sound as it moves away are very different. And it's similar with light waves. So, for example, if a source of light is moving away from us, and we're located here, you can see that the wave lengths are stretched towards us, but due to the motion of that source away from us. So the wavelengths grow. That means the light goes towards the red end of the spectrum, hence the word redshift. If we happen to be on the other side, the wavelengths are being crowded up as the source moves towards us. The wavelengths are decreasing, and you have a shift towards the blue shift. And what Hubble did was to look at the spectra with the atomic lines in them for, say, a nearby star, then a galaxy of intermediate distance, and then increasingly distant galaxies, to find that the characteristic lines, these atomic lines, were being shifted towards the red end of the spectrum the further away the galaxies were. And the distance of the galaxies was determined by their brightness. So the further away they were, the fainter they were. And so this very clever piece of detective work actually led to the conclusion that galaxies are moving away from us and moving faster away from us the further away they are. The space that the universe is made of is actually expanding. Now, we've come a long way since the 20s of the last century in mapping the sky around us, mapping the cosmos. These redshifts, the redshift evidence from distant galaxies is now being accumulated automatically, and the state-of-the-art surveys, there are two of them. One is just completed recently. It's called the 2-degree field redshift survey, or 2DF for short. This is an Anglo-Australian survey which mapped the redshifts of 250,000 galaxies, and it's now complete. I'll show you a little movie shortly of the simulation of the sky which has been gathered by this instrument. And then there's another, even more ambitious and more technically advanced survey which is currently underway. It's mapped about 200,000 galaxies so far, I believe. It's due to map the redshifts of 1 million galaxies. And that's the Sloan Digital Sky Survey, SDSS. And here you see a picture of the automatic telescope, which is mapping sections of the sky and automatically recording the redshifts for 1 million galaxies. It's in the process of doing that. If I'm lucky, this movie from the 2DF survey will work. So this animation was, first of all, you see the satellite. Oh, no, you don't. I see it, but you don't. Okay, well, I'm afraid that's not going to work then. I had a very nice animation of the survey. For some reason, it's not come out. Pardon? I could, yes. I don't know how large it's going to. Let's just try it, and if it doesn't work, you can tell me. Minimize? See, it's on my screen, it's not purple, as it is there. So, obviously.
When you first opened it and it was minimized, you could see the picture.
So, what do you suggest I do?
Close it and reopen it.
Close it and?
Close it, reopen it.
Close it and reopen it. One more time, okay? It's a bit small. Okay, let's make do with that for the minute. This is the telescope, and that's the instrument, the 2DF instrument attached to the telescope. And this is a supercomputer simulation, which is a 3D reconstruction of the 250,000 galaxies whose position has been determined by their redshift information. So we're taking a computer simulated journey through 250,000 galaxies. You can see how they're distributed relative to each other. I could speed it up somewhat, but I don't think I should interfere with it now that it's working. As this progresses, we'll sort of go above the whole slice through the sky, and you'll see something more about the structure, the way in which galaxies are distributed relative to each other. But as you can see, this is an extremely detailed picture which has come from this automated survey. It's not a picture of all the galaxies in the sky. It's just a particular slice in a narrow field in the southern hemisphere, but it's thought to be characteristic of what we would see. Now, as the simulation proceeds, sometimes it'll go a little bit above and sometimes below, and then eventually we will come to see the two slices on the sky that have been surveyed from above. As we're watching those galaxies, you'll see that there are numbers of different shapes of galaxies as well. Some are spirals and some are more elliptical. As we go further out, we're going to older and older galaxies. And shortly, as we go past, there are a couple of spirals that we're flying through. As you go through this, you can't get a picture of how the galaxies relate to each other. Now we should come around and have a look at the slices in the sky from above. And as we look at them, so those are the two slices in the sky that were surveyed by this instrument. You can see how the galaxies cluster together, and you can see the presence of some large gaps. And shortly, some of the shape is going to be traced out in blue form for us, showing how galaxies cluster and how large voids, you get huge walls and huge voids in between the galaxies. And then the end of the survey is just to show what part of the night sky. Here's the Earth, with Australia down here somewhere. There's the one slice at the one end of the sky and another slice at the other, just to give you an idea of what part of the sky was actually mapped by this instrument.
Approximately how far out were the furthest of those galaxies?
They went out to a redshift of less than 1, so no more than 1, the redshift. But that's pretty far out. It's a good few billion light years, the furthest. So that was due to the Swinburne Center for Astrophysics and Supercomputing. I don't know why it only worked when it was small, so I apologize for that. Now, that question has just led me on to the next point, and this is a very fundamental point, but it's an inescapable point, and it arises from the fact that light travels at a finite speed. Although it travels at extremely fast at 1 billion kilometers per hour, it's not instantaneous travel. And so if you think about it, if galaxies are very far away from us, the light is taking a long time to reach us. So the furthest galaxies, that's billions of light years. The light that reaches us is telling us what the galaxy was like billions of years ago. So we're seeing the galaxies in the past. We can't see them in the present if they're very far away from us. And then the question arises, how far can we actually see? Obviously, we have technological limits in terms of faintness of light. Some of our detectors, the detectors are getting better and better, but eventually you go below the threshold of detection. But in principle, how far can you see? Well, that really depends on how old the universe is. The universe can't have in it galaxies which are older than itself. And the age of the universe is about 14,000 million years. So we certainly can't see further back than 14 billion light years. And in fact, as I'll explain a little bit later, we can't quite see as far back as that because in the very early epoch of the universe is opaque to us. So we can actually see about 13 billion light years away. In principle, that's the furthest we can see. Now, a good analogy for that is if you forget about the cartoon on the left for the minute and think about the one on the right, if you look up at the sky on a cloudy day, you know that all you can see is the bottom of the clouds. You can't see through the clouds to the sun behind or the moon or whatever aircraft flying above the clouds. All you can see is the bottom of the clouds. Now, that doesn't mean there's no light in the clouds and above the clouds. It just means that the light that is in the clouds and that is trying to reach us from above the clouds is being scattered by the cloud, and all we can see is the photons that reach us the last time they were scattered from the bottom of the cloud coming down through the empty atmosphere to us. Obviously, it's not exactly empty, there's dust in there, but essentially, light is free after it's last scattered with particles in the cloud. And the light that has been scattered deeper into the clouds, we can't see it because it's being scattered all over the place. It's not reaching us directly. Now, the same thing happens in the universe. If we go back in time, starting at 14 billion years, which is now, and I draw a diagram going back in time towards time equals 0 at the beginning, as we go back in time, because the universe is expanding forward in time, if we go back in time, things are getting closer and closer together, and so the universe is getting hotter and hotter. Now, as things get hotter and hotter, they start to evaporate. And eventually, when the temperature gets high enough, the stars will evaporate. They'll be blasted. They won't be able to exist at very high temperatures because they need a certain threshold of coolness to be able to condense. And eventually, when the temperature gets high enough, atoms cannot form. Atoms are blasted apart by high enough temperatures. So we get, at a certain temperature, which is about 300,000 Kelvin, which corresponds to characteristics of hydrogen atoms, this is roughly the temperature at which hydrogen atoms are ionized. You can't actually form hydrogen atoms, it's too hot. And it's well known in physics that if electrons are free of atoms, they're very efficient at scattering photons. And so at higher temperatures or earlier times than this point here, which is similar to the edge of the clouds here, the photons cannot reach us because they're scattered very efficiently by electrons and other particles. And it turns out that that point is about 380,000 years after the beginning of the universe, so it's over 13 billion years back in time. That's the furthest we can see in principle. And later on, I'll come back to this very important last scattering surface because it contains the most important information that we have about the universe. I'll come back to that in a minute. As I was saying, it's profoundly important conclusions emerge if we think about running the whole movie of the universe's evolution backwards in time. So let me say that once again. As Hubble showed, and it's been subsequently confirmed many times, the universe is expanding. Now, when things expand, they cool down, and the universe currently has a temperature of about 3 degrees Kelvin above absolute zero. It's very cold, and it's getting cooler with time. But if we run this picture backwards in time, we see that particles are not moving further away from each other, they're moving closer to each other if we go backward in time. As things get closer to each other, they become hotter, the temperature begins to rise, the universe gets hotter. And at the same time, when the temperature, if we continue this process to high enough temperatures, as I said, not only stars, but eventually atoms are going to be dissociated by the high temperatures. They won't be able to stay together, they will be unstable, and they'll be evaporated or blasted apart, if you like. What I've got here is a computer simulation of the formation of galaxies in the universe, starting at some very early time when you can see a relatively smooth distribution of matter, essentially because the temperature is very high and things like stars and atoms can't form easily or at all. As the universe expands and the temperature drops, matter begins to accumulate together in little lumps and eventually to start forming stars, and then the stars collect into galaxies, and the galaxies collect into clusters. If I run this backwards in time, I get smoother and smoother picture of the universe. So the conclusion here is that the very early universe is an extremely hot plasma and a very smooth plasma because no structure can really form. The temperature is too high. Everything that tries to condense is dissociated by the high temperatures. And so we run into a very important question. How then did structure emerge? If we run the movie backwards, we end up with a very smooth universe, and we can't really explain how we ended up with galaxies. So that's one of the big questions that we need to answer by looking at the early universe. We see around us billions upon billions of stars and galaxies. We see evidence that the universe is expanding. How did this begin? Where did it all come from? What started this process? Why is the universe the way it is today? In order to do that, in addition to observations by astronomers with their telescopes and by automated surveys like the Sloan and the 2DF, we also need theory, not just observations, but also theory. We need to understand the two fundamental ingredients in the universe. The one is gravity, which is a force which tries to bring matter together by attracting particles to each other. It's the force that keeps us on the surface of the Earth, for example. And the other thing we need to know is how matter behaves. We need to understand how light particles and other particles, such as electrons, behave, how they interact with each other, and in particular how they interact with gravity, in the presence of gravity. So we have a very well-established theory for understanding gravity. That's Einstein's theory, and I'll say a bit about that. And then we have also very well-established theories of theory of particle physics to help us understand the behavior of matter. And those are the two key ingredients that we need in order to uncover secrets of the early universe. So let me move on to a brief discussion of some of the ideas behind Einstein's theory of gravity, his so-called general relativity theory. The key idea in qualitative terms that Einstein came up with, and it was a truly revolutionary idea, is summarized in the blue box there. It's a kind of dual relationship between space-time on the one hand and matter and energy on the other hand. And you can put it, as I've put it in the box, that space-time tells the matter or the particles how to move by the nature of its curvature, if you like, or its geometry. And at the same time, on the other side of the relationship, the matter is telling space-time how to curve. This was Einstein's fundamental idea, which revolutionized our understanding of gravity and which allowed us to actually, for the first time, begin to theorize the nature of the universe, because it turns out that Newton's theory cannot describe the universe. It's just a nice little quote here from Einstein, where he says, "It is my disposition for abstract and mathematical thought and my lack of imagination and practical ability which led me to this theory." It's a rather strange self-assessment by Einstein, because most people would agree that his theory is full of imagination and requires considerable practical ability, but Einstein's own judgment was somewhat different. Well, what can we say about the geometry of space-time and the nature of curvature? I'll just try to give you some qualitative ideas about that. There's a picture of famous geometer Euclid on this slide here. And Euclid described very well to us the familiar three-dimensional geometry of the space that we live in a sense, that we're used to from our everyday experience. So in this room, if I want to locate a point, I'd say at the end of that table, I'd have to give the length of this table over here, and then its width there, and then the height of the point above the table. So I've got three spatial dimensions. And Euclid's geometry tells us easily and efficiently how to deal with those three spatial dimensions. But in the early part of the 20th century, due to Einstein and others, and particularly to Minkowski, it was realized that the old idea of Newton, that time and space were somehow rigidly separated from each other, was incorrect, and that one needed to incorporate time much more intimately into its relationship with space. And Minkowski came up with the idea of a combined space-time. The time and space could not be separated from each other, but we had to think of the world in truly four-dimensional terms. And so the key idea here is that in order to locate an event, you not only need its particular position at one time, you need its position at all times. So you need the time as well. And here we have a slicing of space-time into constant time slices so that we can track the evolution of some event. And if we want to describe, sorry, I'm pointing at the screen, which is a bit stupid. If I want to describe that event over there, I have to give not only its space coordinates down here, but also its time, the time at which it happens, given by how high we are up the time axis. And Minkowski has a nice quote here to exemplify what I was saying earlier, that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Now, of course, that's not true for everyday life, because in everyday life we can separate time and space quite successfully, but to understand the universe, and especially the early universe, one has to follow Minkowski's advice here. Everybody has some notion of the fact that space-time is curved in Einstein's theory, as I was saying in the box previously. So let's just have a look briefly at what we mean by curvature. The key person here is Riemann, whose photo is shown on the slide. And Riemann developed the theory to understand the curvature of spaces. I've just got a small series of cartoons to give you an idea here. The flat space that we're familiar with and that Euclid analyzed so well is characterized in particular by a well-known property that if I draw a triangle in that space and I add up the angles, they add up to 180 degrees. But suppose that the space I live in were not flat, but it were curved. It were either positively curved, like a sphere, which is a closed space, or negatively curved, like a saddle, which is hyperbolic or open space. And then you can understand curvature in the simple triangular terms by drawing a triangle in those spaces. If you draw a triangle on the sphere and you add up the angles, they're always greater than 180 degrees, which is a sign of positive curvature. If you draw a triangle on a negatively curved space like a saddle, it's not hard to see that the sum of the angles will always be less than 180 degrees. And so this gives a bit of a flavor for the consequences of having curvature in a space. You get very different properties. For example, furthermore, if I were to set out on a journey on a closed space and to walk in a straight line, eventually I'd come back to where I started, which is impossible clearly in these other two kinds of spaces. And so from these simple examples, one can get the idea, this essential idea, that the curvature of space can be very important in determining the properties of the universe. It's one of the things that we need to try to uncover is what is the curvature of the universe. I'll come back to that. Now, after Minkowski's idea of the four-dimensional space-time, Einstein came along with the idea of curvature, which was due to the presence of matter. So this was his revolutionary new understanding of gravity, revolutionary in relation to Newton's understanding. And then the next major development was due to Friedman in the 1920s, where he came up with a solution of Einstein's equations which exemplified an expanding universe. And so I have the same cartoon here again. And just to remind you, each instant of time corresponds to a three-dimensional space, as in the previous diagram, but the difference here is that now the space is actually expanding as time progresses. And so Friedman showed that Einstein's theory actually had within it the capacity to explain the expansion of the universe, which was a major step forward, although the significance of this was only recognized a number of years after Friedman's discovery. Einstein himself ignored this development for a number of years. He was a bit behind the times on that one. And Friedman's equation, which is really just Einstein's equation in a particular context, I said I had no equations. This is an equation, but it's actually not a proper one, so don't worry. If you'll remember back to an earlier slide when I mentioned Hubbles Law of expansion, there's a thing called Hubbles expansion rate, which just tells us how fast the universe is expanding. It could be expanding slowly or very quickly. So the Hubble expansion rate tells you how fast it is expanding. And the Friedman equation says that this is determined by three ingredients. First of all, by the matter in the universe, how much matter there is and what its properties are. Secondly, by the curvature of space. Are these sections here flat or closed or open? And thirdly, by a strange and wonderful thing called the vacuum energy, which is something that quantum field theory tells us exists. There's an energy in the vacuum. I'll come back to that later on. So these three ingredients determine the Hubble expansion rate, or how quickly the universe is expanding. Now the question for us is, okay, that's the theory, but what is it that's going to help us to determine these four ingredients in that equation? The expansion rate, the matter, the curvature, and the vacuum energy. How do we determine these quantities? Well, this is where we come back to the last scattering surface that I was describing earlier, which is analogous to a cloud in terms of how far back we can see. This is called the cosmic microwave background radiation. So if you take your minds back to a few slides earlier, as I said, as we go back into the early universe, the temperature is rising and rising. And when we get to about 3,000 degrees Kelvin, that is the last moment at which photons are traveling freely towards us. At higher temperatures or earlier times, the photons are being scattered regularly by electrons, and so the universe becomes opaque to us. But at the instant where the photons last scatter, they travel freely towards us over 13 billion years, and they carry a tremendously rich and important fossil record of what the early universe was like towards us. So they carry a frozen picture towards us of what was happening in the very early universe. We all have heard about the Big Bang, which is the beginning of the universe, when the universe came into being at some extremely high temperature and energy. We can think of the cosmic microwave background radiation as the afterglow of the Big Bang. So if you have a huge explosion, you have a shock wave coming out, but since the universe is expanding, the temperature of that electromagnetic shock wave, if you like, is dropping, so that today it's down to 3 degrees Kelvin, as I mentioned. But earlier in the history of the universe, it was much hotter. And this little picture on the right here shows one of the recent balloon-borne experiments which mapped a region of the sky, mapped the temperature of the cosmic microwave background radiation, and you can see the all-important little variations, the hot spots and the cold spots. Now, I should say that the variations that you can see here are down to 1 part in 100,000, so it's extremely high precision technology that was able to measure these tiny variations in the temperature of the sky around 3 degrees Kelvin. I didn't mention this, but it was actually in 1967, Penzias and Wilson, who are pictured over here, discovered this microwave background radiation by chance. They were actually telecommunications engineers, and they couldn't get rid of a hissing in their instrument until eventually they discovered that this hissing was coming from the universe. It was unremovable. Somewhat unfairly, they won the Nobel Prize for that. It seems a bit unfair to win the Nobel Prize for an accidental discovery, but nevertheless. Now, in 1990, NASA sent up the first satellite whose aim was to measure the temperature of the sky. Had very high-tech instruments on board, because you can imagine that in order to do this, you need the latest technology. At the time, this was at the cutting edge of technology. And there's a schematic of the COBE satellite, the Cosmic Background Explorer satellite. What it found, first of all, was that the temperature of the sky was 2.7 degrees Kelvin. Not exactly 3, 2.7. And that radiation was a black body to incredibly accurate degree. It's the most perfect black body ever measured, and measured to an incredible degree of accuracy. But on top of that 2.7 degrees Kelvin, there are two corrections. First of all, there's about plus or minus 3 millikelvin redshift due to the motion of the solar system, in fact, of the local group of galaxies in the cluster. We're actually moving at about 1.6 million kilometers per hour relative to the rest frame of the universe. And this is just another Doppler effect, so that one end of the sky appears cool and the other end of the sky appears hot. So we have a redshift simply due to the fact that we are moving relative to the universe. We're orbiting the sun is orbiting the center of the galaxy is orbiting around within the local cluster. And when you correct for all those motions, you can get rid of this dipole. But much more fundamentally, what's left over once you've corrected for the dipole are intrinsic ripples in the temperature. Now, they're even smaller. They're at microkelvin level, 1 part in 100,000. So you've got this temperature of 2.7, and then at 1 part in 100,000, you have these little ripples in the temperature with some colder spots in the blue and some hotter spots in the red. This big red slice through the middle is just our galaxy, which messes up the observations. That has to be cut out. And what that is telling us, and for the first time this was confirmed in just after 1990, it took about 2 years to process the data, it was about 92. what this is telling us is that the very early universe, when it was extremely hot, was not perfectly smooth. So there were already these little ripples. And that's very important because these ripples are going to be crucial for us to understand how galaxies emerged, as I'll explain shortly. Now, COBE was launched in 1990. There were a number of experiments followed it, but the next satellite experiment was the Wilkinson Map satellite, which was also a NASA experiment. The data was first released from that just under a year ago, and you can see the tremendous increase in precision. If you look at the detail on this map compared to the previous map, you can see how the technology has improved in those 10 years since the first flight, and we have a much more accurate and much finer detailed picture of the temperature fluctuations on the night sky. So what we're seeing here is a picture of the surface of light scattering. This is a frozen picture of how the universe looked in terms of light at a mere 380,000 years after its beginning, more than 13 billion years ago. And it turns out that the nature of those ripples and how they are distributed across the sky contains vital information for us from the early universe. Now, if you think about the surface of light scattering, what was happening at the time of light scattering were two competing forces in the early universe, and these competing forces persist throughout the history of the universe. But at this time of light scattering, the two forces were more or less in equilibrium. On the one hand, we had gravity, which was trying to condense the matter together. And on the other hand, we had the pressure due to radiation, which was trying to blow the matter apart, because it was quite hot, 3,000 degrees Kelvin. And these two forces were more or less in equilibrium, so that the universe was oscillating. Some trying to fall in and then being pushed apart, pulling back, pushed apart. So we had the universe, in a sense, like a large bell, oscillating at a characteristic frequency. And the frequency of oscillation has vital information for us about the vital statistics of the universe. Just like the frequency of a musical instrument can tell you crucial things about its physical characteristics. But there's one important additional ingredient which is not present in the case of musical instruments, and that is this last point here, that not only do we have this characteristic frequency of oscillation, but the light which travels to us over 13 billion years is traveling through a curved space-time. And the nature of the curvature, is the universe flat, is it closed, is it open, will have crucial implications for us because it can process or distort the information being carried by the photons. And if I'm lucky, I have a movie from the NASA website which will show us this schematically. Okay, so this is a simulation which... Oh, no. It's purple again. One more try, perhaps.
Try to resize it before you play.
Try to resize before I play. Okay. So, smaller.
No, just drag. Go to the top.
Yeah.
Drag down. Go to the top, bottom right. Bottom right. Press on the bottom right.
Yeah.
Try and pull it up. Yeah, there you go.
Close and open again. This is really... Also ask me every time if I want to actually play it, which is a bit of a nuisance. No, it looks like this one's not going to work. Minimize it. I think I shouldn't have done that. You can see I'm rather technically challenged. I seem to have lost it altogether now. No, perhaps I won't bother with it then. I should perhaps be... now I've got this bar at the bottom.
Just
Click on it.
No, click. That one on your screen. Not there.
I'll get there. Right. Perhaps I should be satisfied with one animation that worked or half worked. So I had an animation to show you how the nature of the geometry affected it. I'll just have to wave my hands a bit and repeat to you that if the light is traveling to me from 13 billion light years away and it's traveling through space which is curved positively like a sphere or curved negatively like a saddle or flat like a Euclidean space, that light is going to be affected. And so the last scattering surface, the ripples that we see on the last scattering surface, they're going to change their relative position, those ripples, due to the intervening geometry. So we not only have the effects of what was was happening in the early universe 13 billion years ago. There's a frozen record in there, but they're also processed by the intervening curvature of space, which Einstein's theory tells us exists due to the nature of gravity. Now, as I've mentioned, the ripples across the night sky have a certain distribution. How many hot spots, how many cold spots, how large are they, how do they cluster together? What is the overall shape of the ripples in the temperature of the night sky? And the things that decide this are, as I've said, the shape of the universe or its curvature, the weight of the universe, if you like, what kind of matter is in the universe and how it's behaving, and the age of the universe. I've mentioned that the universe is 14 billion years old, but until we knew that, we simply knew that the actual age would determine the distribution of these ripples. And once we'd worked that out, we've got the answer. So we can take it from there. But to describe to you what are the ingredients, those are the ingredients. Roughly speaking, the shape and the weight and the age of the universe. Now, having processed the information in those ripples, and this is a huge enterprise, takes years to do that, but at the end of the day, the conclusions are the following. These 4 bullet points that I've collected here. First of all, the curvature of the universe, or its shape, the evidence is that it's very nearly spatially flat. So it's quite boring in a way. It's not dramatically curved in one positive or negative way. It appears to be actually flat. So that's quite surprising in some senses. You may have thought the universe should be more complicated, but the evidence is that the geometry of the universe is fairly simple. And that's an important piece of evidence and information for us. Secondly, we discover that most of the matter in the universe is not what we see through our telescopes because it's not luminous. So most of the matter in the universe is not shining. Most of it is not in the form of stars, which make up the visible part of galaxies. In fact, 80% of the matter is invisible to us and is hence dubbed dark matter. So that's a very surprising and intriguing feature which arises from the observations. And then even more surprising and more dramatic is that not only is most of the matter dark, but the matter itself is really not the main ingredient in the universe. The vacuum energy that I mentioned before dominates over the matter, and that makes more contribution to the universe than the matter on its own. And that is even more surprising. This vacuum energy is sometimes called dark energy because it is also dark in the sense that we can't see it. And finally, as I've mentioned before, the universe is about 14 billion years old. Now, I've talked about these ripples on the night sky, and here I've got a 3-dimensional picture of the night sky rather than the flat projection which I showed before. The question is, what happens to these ripples? And the most amazing thing is that these are the ripples that form the seeds of galaxies. And the idea is really rather simple. If you think about what these ripples are, the red spots are spots which are a bit hotter. That means there's a bit more concentration of matter there. And the blue spots are where they're colder. That means there's less concentration of matter. They're under densities. And what gravity does is it tries to pull matter together. It's attractive force. It's universally attractive. So if I have a region around me here where there's a bit more matter, it will tend to suck matter from surrounding emptier regions towards it. So this overdense region will get more overdense, and the surrounding underdense region will get more rarefied. And if you allow gravity to do its work, it's a slow and weak force, but it's inexorable, relentless, and irreversible. If you give it a few billion years to work on these tiny ripples, which remember were 1 part in 100,000, very, very tiny ripples, but you give it a long enough time, the condensation of the overdense spots and the rarefaction of the underdense spots gives us the fantastic network of galaxies and clusters and voids that we saw in the previous animation. So these ripples, which took us so long to find and required the highest technology and supercomputers to get the information out of, they are exactly the things which give us the seeds to explain the presence of the galaxies. So we've kind of killed 2 birds with 1 stone there. And that is one of the great triumphs of modern cosmology, allowing us to connect the very early universe with this frozen fossil record here to the late universe with its mature development of clusters of galaxies and their distribution relative to each other. But then we have to ask the following question: where do these ripples come from? And the currently fashionable answer, although it's not a definite answer but a very intriguing answer, is that these ripples come from the quantum vacuum. Now, most of us think of vacuum as nothingness. There's nothing there. But actually, in quantum theory, we learn that there's no such thing as nothingness. The vacuum is actually alive with all sorts of things that are happening. Virtual particles emerge and then annihilate and disappear all the time. The quantum vacuum is seething with fluctuations. It's rippling, if you like, just similar to the ripples that I've been talking about, but of a quantum nature. And furthermore, also very interestingly, the quantum vacuum has a negative pressure. And what the negative pressure does, if you look at Einstein's theory of relativity, or gravity, it drives a very, very fast expansion of the universe. So the quantum vacuum can explain two things to us. First of all, it can tell us where the ripples come from. And secondly, it can initiate this expansion of the universe, which is observed by Hubble 13 or 14 billion years later. So it's a very intriguing answer. We're not sure if it's correct, but it appears to be able to kill two birds with one stone again. And here I have the previous cartoon, but distorted by the ripples. So you can see instead of having perfectly smooth three-dimensional space surfaces, they're now subject to these ripples, which are initiated by the fluctuations in the quantum vacuum. And the nature of the vacuum itself drives a very rapid expansion of the universe. The universe expands extremely rapidly, and therefore that early period of the universe's history has been dubbed inflation because of the rapid nature of the expansion. It's actually an accelerating expansion. So this cartoon then tries to summarize the key events in the history of the universe. If we run it backwards in time from the current universe with its formed galaxies and clusters, one of which we live in, if we go back to 380,000 years after the beginning of the universe, we have the fossil record of how the universe looked in the temperature ripples of the radiation, the cosmic microwave background radiation. If we go back, the current theory suggests that in a very tiny fraction of a second after the beginning, we had this rapid expansion of the universe, this period of inflation, which not only blew the universe up to a large size, but also generated the ripples that we see here. But of course, that begs a further question: what happened before inflation? There's a big question mark there, which is still largely unanswered. So the question that I'll end up with really is, what about before inflation? So if we go back in time to the very, very earliest epoch in the universe, we quickly realize that we have to move beyond Einstein's theory. Einstein's theory can't help us once we get to high enough energies. The energy is just too high before inflation, and Einstein's theory breaks down. And a lot of ideas over the years have been floated. There's been a lot of speculation about what might happen before the Einstein period of the universe, if you like. A currently fashionable set of ideas goes under the name of the brain world universe theory. This idea involves the notion that, in fact, the three spatial dimensions that we're aware of are not the end of the story, and that the universe actually has extra spatial dimensions that we just don't happen to see because we're living at low energies. But if we go back in time to higher and higher energies, these extra dimensions, which are currently invisible to us, become visible, although we're not alive then, so we don't actually see it, but they become as important as the three dimensions we live in, and gravity behaves very differently. Instead of behaving like a four-dimensional interaction, it starts to behave like a higher dimensional interaction. So the idea here is that our universe is actually a surface embedded within a higher dimensional true universe. The universe that we think we're observing is actually just part of the actual universe, which is sitting in a higher dimensional space. And these brain world ideas come from something called string theory. String theory suggests that fundamental particles are not points, but they behave like strings, and the vibration of the strings gives the different vibration modes of the strings give different kind of particles. And strings come in two varieties. You have either open strings or closed strings. The closed strings represents the gravitational interaction. The open strings represent the matter that makes up galaxies and the light, the photons that make up light. And these closed strings, open strings rather, have their ends attached to our observable part of the universe, whereas gravity is allowed to access the extra dimensions. So as I've said here, observable matter lives on this four-dimensional surface, which is called a brane, after membrane, and gravity will propagate in the higher dimensional universe, which is sometimes known as the bulk. It's not clear that this is actually going to give us the answers to what happened before inflation, but it's an interesting set of ideas which is currently being looked into. And essentially, we're running into the limits of our understanding of the universe here, and we're starting to need to speculate as well as trying to apply theories which are really not able to be applied at the edge of their applicability. But nevertheless, a whole set of new and exciting ideas is beginning to emerge. At the same time, as I think I've conveyed to you, the observations are getting increasingly sophisticated. The data that we're getting is of increasingly high precision and quality. And as the observations continue to come in greater volume and of greater precision, we're going to find out more about the universe, not just more accurate measurements of these various quantities, but we're going to discover new things. We should begin to discover just what the dark matter is made of. We should begin to find out more things about this mysterious dark energy, or the vacuum energy that I've talked about. And undoubtedly we'll have a whole host of new surprises that will be uncovered by the observations. So for those of us who work in the theoretical side of cosmology, trying to close the loop by supplementing observations with theory, the challenge for us is to try to catch up with the observations. There's been a theme through my talk which can be expressed in the fact that observations are running ahead of theory. Theory is currently unable to account for all of the wonderful bits of information that are being thrown up by the data. And so theory needs to do a bit of a catch-up here. It needs to keep pace with the observations. And essentially we need to come up with some quantum gravity theory which takes us beyond Einstein's theory, which is not a quantum theory. And hopefully once we do that, we'll begin to understand the earliest bits of the universe, inflation and before inflation, which will take us right back to the beginning. And I'm sure even then we will have more that we'll need to uncover, but that's a good point for me to end. Thank you.
Any questions?
I read a while back that they were unsure of what would happen to the universe sort of in the future, whether the Terra would continue to expand or whether it would crash, depending on how much of this dark matter they found. But that was a while back. Does this sort of amount they found now tell us anything about the future in that way?
The observations currently can't distinguish between the possibilities into the future. The observations simply tell us that there is enough dark energy to be accelerating the universe currently. The universe is accelerating, and it has been accelerating for a while, but a very short while in terms of the history of the universe. And what you read about was really the subsequent question. Depending on what it is, or the properties of this dark energy, depending on the properties of the dark energy, the universe could do one of three things. It could either continue accelerating forever, so that eventually all the galaxies are blasted apart and we just end up with a cold desert universe where no life could survive, because the accelerating expansion is overcoming the tendency of gravity to pull matter together. That's one option. The second option is that the acceleration eventually comes to an end and the universe resumes its decelerating expansion, its slow expansion. That's the second option. And the third option is that the universe actually not only stops accelerating, but it turns around and starts to collapse. So there are various models which predict that the universe in the future will actually collapse. In fact, there's particular models called cyclic universe models in which it's theorized that the universe goes through cycles where it comes into collapses, and then it goes through a bounce and starts to expand again, structure forms, the galaxies form, it collapses, all the structures are melted together again, it bounces, and so it carries on forever, expanding, collapsing, expanding, collapsing. So these are all speculative ideas, and the three options, which of the three options it's going to be, well, currently the observations can't tell us. It's hoped that the next generation of observations will have sufficient information to begin to tell us whether the acceleration curve is carrying upwards, is flattening off, or is turning over. For the moment, we don't know.
Which of the three options coincide with the facts that, or the statement that future is the Sitter space? Malik said future of the universe is the Sitter space. Which of the options?
That is the first option, the one where it accelerates forever. So it becomes a cold desert.
There's some talk recently about a new repulsive force, the possibility of such a thing. Is that the same as Dark?
Yes, that's exactly right. It has an anti-gravity effect, essentially, because it has a negative pressure, a very negative pressure.
This question's a bit tangential, but it came up in our discussion group yesterday. A lot of the cosmology we've seen treats the universe as a homogeneous fluid. That clip we saw of the map of galaxies all the way out to a redshift of 1 didn't look very homogeneous at all. How is that not a problem?
Oh, that's a very good question. It's really a question of scale. So if I go down to small enough scales, if I look at on the scale of this lecture theatre, it's certainly not homogeneous. If this were a homogeneous lecture theatre, it would just have a plasma of electrons and protons, neutrons, and photons buzzing around, colliding. But there's a lot of structure in this room. There are human beings which are incredibly complex structures, and tables and chairs and whatever. So certainly on the scale of this room, which was of the order of, say, 10 meters or so, the universe is not homogeneous. It's extremely nonlinear. If you start just stretching out from there, the solar system, the galaxy, inside galaxies is extremely nonlinear as well. But as you start going to larger and larger scales, eventually, on average, things become homogeneous at a large enough scale. And of course, the crucial thing is, how large does that scale have to be? If the scale on which the universe is effectively homogeneous is sort of half the size of the universe, then the universe is not effectively homogeneous. But it turns out that the scale on which the universe is effectively homogeneous is a small fraction of the observable size of the universe. So as long as you average on the right scales, as long as you apply the theory that you're dealing with to the right objects, cosmology describes the whole universe, which is in its observable size is 14 billion light years in radius, whereas things like the astrophysics of stars deal with much smaller quantities, although they're also using gravity and particle physics, and they're dealing with very much non-homogeneous objects. So it's just a question of scale of where you apply the theory.
About 1965, I was working at NITR. This is the radio institute that used to exist in South Africa. And we had the Hubbles Hook tracking station. Now, there was a lot of talk about that time about using, they did use Hubbles Hook to pick up the radio emanations of the black body radiation. It's a very simple formula to take 3,000 and divide it by the peak radiation or by the temperature, 2.7 K. You come to the value 1,000 microns, which is 1 millimeter, just on the border between infrared and radio waves. Now, at that time, it was always said that this radiation was due to the hydrogen-ion radiation. Is that theory still holds? That the radiation is due to the heat of the hydrogen molecules, which in the early days, the only dark baryons, the only dark matter was hydrogen. Helium hadn't formed yet, and the heavier elements.
Well, the ratio between the temperatures of 3,000 Kelvin and 3, which is 1,000.
Yeah, 1,000 to 1.
That actually gives the redshift back to the last scattering surface. So a redshift of 1,000, which is a huge redshift if you think about it, is the redshift between us and the last scattering surface. So the furthest galaxies in those surveys are around about a redshift of 1. Some individual galaxies have been picked up at redshifts of order, say, 3, 4, up to about 5 even. Some quasars, quasi-stellar objects of redshifts of 5 or 6. So you think a redshift of 1,000 is very, very far away. So I'm not sure why the ratio of the two temperatures is dimensionless, so I don't get a millimeter there, but maybe I misunderstood you.
Well, I'm thinking of the Planck's black body equation. You know, they
Yes.
call ultraviolet catastrophe, which was a solid like Einstein. And you get that shape of the black body radiation.
Yes. Yes.
It goes up steeply. It goes to infinity there.
Yeah.
It goes up and goes down with a very gradual one. This is in a log scale this way.
Yeah.
And the peak radiation, where it's maximum, is a very simple formula, which doesn't seem to be widely known. You take 3,000 and divide it by the temperature, and you get the radiation at the peak. And that corresponded with a hydrogen-ion radiation. Now, that a lot
Yes.
was talked about
Yes.
that in 1965, 1966, when it was first discovered. Has it now dropped away? Don't you consider that anymore?
Well, essentially, I think this must be to do with the fact that the radiation we're looking at last scattered at the time
Due to the temperature of
at,
the
at,
hydrogen. which
at
is
exactly the energy that hydrogen is dissociated, about
there was only
13.
hydrogen at the time.
Yes. Now, there's contaminations of helium, but very, very much subdominant.
Very small proportion of helium. Now, if you have to wait a few thousand years, maybe you'll see the helium come up. Well, more than 5,000 years.
Well, people have actually looked to see what the influence of this small bits of helium would be on those ripples, for example. So that has been looked at. It's a very small correction.
But this is the kind of thing they're looking at, is it?
Yes. Roughly speaking, yes.
One of the causes of the ripples why heavy elements would be formed, helium, then lithium, beryllium.
Well, in the very early universe, before the last scattering event, at a much higher temperature of about 10 to the 8 or 10 to the 9 Kelvin, say 1 billion degrees Kelvin, you had the first nuclear synthesis of nuclei rather than atoms. And nuclear synthesis predominantly, obviously, manufactured helium, but also significant amounts of deuterium and lithium. The other elements, the heavier elements, are manufactured in stars. So stars are the factories for manufacturing the heavier elements. But of course, lithium and deuterium and helium nuclei were around at the time of last scattering, but not atoms. Not sure if I answered your question.
Just the idea of the curvature of space, the open, closed, or flat. I mean, you've obviously kind of interpreted that in two-dimensional space, then
Yes.
closed it or opened it away. But I mean, kind of how would that be observable in terms of three-dimensional space?
Well, the three-dimensional case is the surface of a three-sphere. Now, you can't actually imagine that because you need to think in 4 dimensions to draw the surface of the three-sphere. So the actual picture of the sphere is not really misleading. It's quite a good representation of a three-dimensional closed constant curvature space. The flat plane is a good representation of a three-dimensional flat space. It's just you've just suppressed one of the dimensions. The saddle is much more difficult to imagine. What a three-dimensional saddle surface is, I have no idea. I mean, a three-sphere is hard enough, but it has the same shape as a two-sphere. What the shape of a saddle is, I don't know. That's a tough one.
In terms of, I mean, what would it do to a beam of light that I'd expect to go straight?
Oh, okay. So what you have to think of is if you have a beam. Let me see. I suppose I could draw this. If I have light reaching me from some event, so say this is a piece of the last scattering surface, and I've got a whole lot of light coming to me from the boundaries of this. This is how the light would propagate if the curvature is zero, if the space is flat, essentially in straight lines. But if the space is curved, then light is going to do something like that. And so what's going to happen is that the angle which you associate with that distance is different. Okay? If I look at this distance in a flat space, I associate it with the solid angle, the orange solid angle. But if space is actually curved, then the solid angle is smaller. So the relationship between angles and distances angles and lengths rather, is radically altered. And interpreting how far something is away from you in terms of angles can be dangerous if you get the curvature wrong. You could also have the other case, another case of curvature. So it's essentially, it involves interpreting how you go from angles to lengths. And the curvature affects that quite importantly.
Will more information about that quantum energy will affect some model of the universe? If it will, how will it affect the present model?
Well, it's hard to say because it may be, for example, that dark energy doesn't actually exist and it's just our current way of understanding a particular observation. And it may be with new developments in theory we realize that there isn't actually dark energy. There's a different theory of gravity, and some alternative explanation for how we interpret the observations may come up. But if dark energy does actually exist, then the observations will increasingly tell us more and more about its properties. And, for example, will begin to indicate what the future fate of the universe is going to be. It's difficult to answer your question because the real answer is we don't know, and we'll have to wait and see.
How does dark energy fit into our current picture of fundamental forces? Would it be a radically different force, or can it be integrated into the current?
It's yes and no. Essentially, dark energy can arise from the quantum vacuum energy or variations of that, so it could be understood in terms of quantum field theory. But the hidden problem in my statement is that when you do that properly, the numbers that you get from your quantum theory and the numbers that we get from the observations are vastly different from each other. So something is not right. We're not sure. So it's certainly, from whatever angle you look at it, if you look at it deeply enough, it's a puzzle. There's something that we still don't understand.